Okay, so now we're at the point where we're going to talk about what does the second derivative tell us about the function. So we talked about that the second derivative tells us about whether the first derivative is increasing or decreasing. But what the second derivative tells us about the function is called concavity. So the second derivative tells us about concavity. So when we made our little picture chart, the ones that looked like parts of a dish turned upside down, these are called concave down. And the ones that look like parts of a dish that's right side up, these pieces are concave up. So this is when F double prime is negative, F double prime is negative. So if it helps, notice that the parts that are concave down look like parts of a frown. They're not the whole frown, they might just be one side, but they're parts of a frown. Down people frown, and down people are negative, so down, negative, frown, those all go together. So then we have the opposites that go together. Positive people are more up and they're more likely to smile. So if it looks like a piece of a smile, it's concave up and the second derivative is positive. So people come up with different ways of making sense to themselves. It can look like part of a bowl that's upside down or right side up. Some people see it as that it holds water or it doesn't. One way of thinking about it is if you were riding on a roller coaster and you're riding on the part that's concave down, you see the sky. And if you're riding on the part that's concave up, you see the track. So that's another way of thinking about it. So technically it's concave upward and concave downward, but people never say that. They say concave down and concave up. And in fact, we're going to abbreviate those and say CD for concave down and CU for concave up. So in this graph, we would say that the graph is concave down, the second derivative is negative, on the interval from negative infinity to b. So on this part of the graph, it's concave down. Then it's kind of hard to see visually where the graph switches from concave down to concave up. It's kind of subtle. So if you're trying to draw it, you'd say, wow, it's kind of somewhere in here. It's hard to say exactly where that subtle shift happens from concave down to concave up. So this graph is concave up on the interval from b to infinity. And then this point where the concavity changes is called the point of inflection. So think about the analog or the parallel with the first derivative. If we found an x value where the derivative was 0 and the sign of the first derivative changed from positive to negative or negative to positive, then we could conclude we'd found a max or a min. In this section, if we find an x value where the second derivative is 0, so the second derivative is 0, and it changes from positive to negative or negative to positive, we call the point where that happens either a point of inflection, so you'll see some calculus textbooks call it POI, and others call it an inflection point. I usually call it inflection point. It's shorter, but if you've learned it POI, that's fine. So if the concavity changes, we have an inflection point. So this is subtly different from the max-min conclusion with the first derivative, where the first derivative, the derivative has to change and the derivative has to be 0 at the point. So let's look at this as a really unusual example where we have f of x equals x to the 1/3. So the first derivative is 1/3 x to the negative 2/3. And the second derivative is going to be negative 2, let me make that better, negative 2/9 x to the negative 5/3. Okay, so I'm going to write that without a negative exponent, negative 2 over 9x to the 5/3. So this is never 0. But it is undefined when x equals 0. So if we were making a chart and saying, here's the x value of 0, we would say the second derivative is undefined here. And then we could check on either side like we've been doing, and we could say, what is f double prime of negative 10? And we had negative 2 over 9 times negative 10 to the 5/3. Well, a negative number to an odd power is going to be negative. So this result's going to be positive. And then we could test on the other side and say f double prime of 10. And that's clearly going to be negative. So the concavity's changing from concave up to concave down. So at x equals 0, we have an inflection point, even though the second derivative is undefined there. So it's a strange looking function. If I drew a picture of it for you, it goes like this, where it goes vertical just for a moment here. So the first derivative is undefined, but the function exists there. And the second derivative is undefined, but the concavity definitely changes. And my picture is not very good because this picture changes from concave down to concave down, but it goes like this. Sorry. So it has a vertical spot there. So the concavity changes and we have an inflection point, even though the second derivative is not defined there. So this will be the point 0, 0, and it is an inflection point where the concavity is changing. Okay, so I have another example for you, and these are just kind of small, subtle examples. We're not going to run into a lot of fine points, but I want you to be aware of them. So here's an example where the second derivative is 0, but the concavity doesn't change. So if I have f of x equals x to the 4th. Well, my first derivative will be 4x cubed And my second derivative will be 12x squared. Well, I can see that f double prime is 0 when x equals 0. Okay, so if I set up a little chart, I would say, let's see, when x is 0, the second derivative is 0. But then look at this second derivative. It's always positive, right? X squared is always positive, and then multiply it by 12, always positive. So yeah, the second derivative is 0 at 0, but the concavity doesn't change. So not an inflection point. So the point of this example was finding where the second derivative is 0 is not enough information to be able to decide you have found an inflection point. You have to check and make sure the concavity changes there. That's the significance of the point of inflection. Okay, so let's do a couple of examples and look at how we actually do the work for this. So this first example, I'm going to rewrite it as -2 times x plus 1 to the -1. Whenever I have a quotient and there's just a number on the top whose derivative would be 0, then I'm always going to rewrite and use the chain rule. I don't prefer to use the quotient rule in this case. So my first derivative is going to be -2 times, bring the -1 down in front, x plus 1 to the new power of -2 times the derivative of the inside, which is 1. So that's going to give me 2 times x plus 1 to the -2. So now I need the second derivative. And it's going to be 2 times -2 times x plus 1 to the new power of -3 times the derivative of the inside, which is 1. So that's going to be -4 x plus 1 to the -3, and then I'm going to write it without a negative exponent. Okay, so this second derivative is never 0. It has a -4 in the numerator, and only numerators make fractions 0, so this is never 0. So then my next question is there a value of x that makes f double prime undefined? And as soon as I say undefined, you should either be looking for a square root that has a negative number in it or a denominator that's 0. So look at this denominator and see when x is -1, f double prime is undefined. So this is the same definition as for the critical numbers of the first derivative. It's anywhere that the derivative is 0 or undefined. So this is our divider on our chart for f double prime. So this is the x value that causes f double prime to be undefined. Okay, so then let's look at our intervals. And we only have 2 from -∞ to -1. So I'm going to use -10 for my test point. Now I'm testing f double prime and asking, is it positive or negative? So if I have f double prime of -10, I'm going to have -4 over -10 plus 1 cubed. So a negative number cubed is negative. Negative divided by negative is positive. So we get positive for the sign of the second derivative when x is smaller than -1. And then let's check from -1 to infinity, and 0 is a nice easy number to check. F double prime of 0 is going to be -4 over 1. So that's going to be negative. So let's see what that tells us about f. Concavity positive means f is concave up. Concavity negative means f is concave down. So it's not that the second derivative is concave up, the function is concave up. So let's go look at the instructions. Find the open intervals on which each function is concave upward or concave downward. So we're going to say f is concave upward on the interval from -infinity to -1. And then f is concave downward on the interval from -1 to infinity. And then it asks if there's any points of inflection. Well, the point we found where the second derivative was undefined is also a point where the function is undefined. So for this example, there are no inflection points because the graph does not even exist when x is -1. In fact, let's take a quick look at the graph, and here's what it looks like. So when x is smaller than -1, to the left of -1, concave up. To the right of -1, concave down. But there can't be an inflection point when there isn't even a point when x is -1. Okay, so I'm going to start another movie to do the next example, so we're not rushed.